Hello, everyone, and welcome to another measurement instrumentation class. Today's class is going to be a review for our upcoming exam. It's going to be next week. I've already sent an announcement for online students as well. And without further ado, let's start with the exam. Before I start, I just want to let you know about the topics in the exam. It's going to be the measurement errors, RMS and the AC power, three-phase power, and also voltmeter and ammeters. These are the topics that we are going to cover in the upcoming exam. Okay, so let's start with the first question. Again, the way we do this, I'm going to give you a few minutes. The first student to solve it gets bonus points on their upcoming exam. Sorry, thank you. And I'll give you 5-7 minutes, depending on the question, for each question to solve. I would like to solve as many problems as I can and give you as many problems as I can. So the first question, a 3-volt source with internal resistance of 0.5 ohm feeds a 10 ohm resistor. An ammeter with the resistance of 10 milliohms is inserted in series. Find the current without the ammeter, the current with the error, and percentage of the error. Yes.
But is are these lecture notes available on the lectures in Office Canvas?
No. This one, the review session, no.
And
I would post them after the class, but no, it's not going to be. I only have the lectures are all, aren't the lectures already on there?
yes, yes.
So these are the exact questions from the lectures. I just changed the numbers or tweaked them a little bit. So if you get do the practice problems or the homeworks, it's going to be very similar to that. In addition to these questions, you're going to have maybe one questions on mean and standard deviation, because that's too easy. I'm not going to go through it in a review session, but definitely go through your homeworks and also the practice problems that we solved in the class. Okay.
Sorry. Is it open note or no?
No, I will give you all the equations that you need, but it's not going to be open book or open note. All the equations that you need would be provided on the exam. Sorry. What is the percentage of error that you found? Has anyone found it? Now you can use your notes. If you're asking about now, yes, you can use your notes, but on the exam, you can't. Yeah. Yes, yes, errors. Perfect. Remind me to give you extra points. Did you all solve it or do you need more time? Yeah, okay. Do you need more time? Yeah, okay. So first thing that we need to do is we want to find the true value of the current without the ammeter. That means the true current that's going to pass. And for that, I can use the Ohm's law. So true value of I would be equal to V over R plus R, which is going to be the 10 ohms plus the resistance of the source itself. That's the current in an ideal situation when we have an ideal ammeter with 0 internal resistance. So if I do that, the current would be 0.285. Oh, so V is 3 and 10 plus 0.5 gives us 0.2857 amps. And by the way, if my calculations are different from yours, just let me know so we can do it. And now the measured value, I'm going to call it I measured value is going to be equal to, again, V. But this time it's going to be R plus R, and I'm going to call this RA, R of the ammeter, which is going to be equal to, again, 3 over 10 plus 0.5 plus RA, which is 10 milliohms, or in other words, 0.001 ohms. And this would be equal to 0.2853. And this, I wanted to, 538 amps. Now the percentage of error would be equal to the true value, I true, minus the measured value, I don't want to confuse it, over the true value, I true, times 100. And if we calculate that, it's going to be 0.28571 minus 0.28538 divided by 0.28571. I don't have enough space to write it down. Therefore, it's going to be 0.11%, or in other words, 0.1% error, if I want to round it. So this was a simple one. I'm going to skip the simple ones so I can solve like the more difficult ones. I'm going to go to question number 4. So this question, a 6-volt ideal source feeds series resistance R1 10K and R2 5K. A galvanometer with a resistance of 60 ohms is connected across R1 to measure its voltage. Find true voltage across R1, the measured voltage, and the percentage of error. Did anyone solve it? Error 2.39.
Is that off?
Yeah. Oh. Zero. Has anyone else solved it? No? Mhm. Do you need more time or do you want me to? Okay. I'll give you another.
It's the actual, that's the person who said.
Error. No. What is the error? What is the error that you found? Okay. Yes.
Not the error, but is there supposed to be that much of a difference? So that's
Yeah.
V1,
Yeah. Can you find the error?
Okay, yeah.
What is the error?
Yeah, I don't know.
Yeah.
I'll just make sure I'm-
Yes, yes. It could be, yeah.
No.
Very close. Okay, can I, do you have solve it, or do you want me to solve it? Yeah. Okay. So one thing to keep in mind, especially when you're taking multiple choice, our exams, like most of the time, it's multiple choice questions, and especially in the FE exam, because in the FE exam, you're going to have 4 or 5 questions of these. Reading the questions carefully is like solving 50% of the question, okay? Now, in this question, what is the galvanometer used for? It's to measure what? Voltage. So we have 2 resistors in series, and we want to measure one of the resistors' voltages, okay? For an ideal voltmeter, so the galvanometer works as a voltmeter, okay? For an ideal voltmeter, what is the internal resistance for an ideal voltmeter? What happens if the internal resistance of the voltmeter is 0 or very low? Perfect. Now, what is the internal resistance of this voltmeter? Compared to the 10K, it's very, very, very small. So if your options for the error were like 1%, 2%, 60%, 98%, which one would be the answer? 98%, yes. Why? Because this is technically short-circuiting your resistor, okay? For an ideal voltmeter, we want that resistor to be infinite, no current passing it, so all the current would be forced to pass the 10K, and therefore we have an accurate measurement. Now let's see if our assumption was correct. Let's solve the problem, okay? So first thing we want to do, we want to find the voltage when we don't have the voltmeter. That's the true value of the voltage of R1. I can do it in multiple ways. I can use voltage divider. If I use voltage divider, V of R1 would be 10 times 6 over 10 plus 5, which is going to be 60 divided by 15 gives us what? 4 volts. This is one way to solve it. Voltage divider. Another way I can calculate the current, which is going to be 6 divided by 10 plus 5, which gives us 0.000. And by the way, all of these in K. 4 or 0.4 milliamp. Therefore, VR1, the true value, is going to be equal to this I times its resistance, which gives us 4 volts again. Okay, so multiple ways to solve it. Now, this is our true value. Now, let's find the measured value by the galvanometer. Now, if we want to do that, we have to first combine these 2 resistors. These 2 resistors are in parallel. So R1 in parallel with RG would be 10,000 times 60 over 10,000 plus 60, which gives us how much? It's going to be closer, less than the smallest. So when you put 2 resistors in parallel, the equivalent or the total resistance is going to be smaller than the smallest one. So this is going to be 59.64 ohms. Now, let's find the total resistance. When we add the galvanometer, it's going to be 5,000 plus the 59.64 ohms, which gives us 5,059.64. Sorry, my pen doesn't have enough space. So this is 0.64. Now, again, we can find the current here. I'm going to call it I prime. It's going to be 6 volts divided by the total volt, 5,059.64, which gives us a current of this sign 0.001186 amps. Now, using this current, I can measure the measured value of the voltage, which is going to be I prime times 59.64 gives us 0.708 volts. Now, if I want to find the percentage of error, it's going to be 4 minus 0.708 divided by 4 times 100 gives us 98.23%. So the result is 98.23%. Okay. Is it clear? Okay. But the easy way, just look at this. If this resistance was, the galvanometer was like 100 mega ohms, or then the accuracy would be, their error would be around 1%, or the accuracy would be 98, 99%. Can I move on to the next question? Yes. Okay. Let's do one on errors. This one. The true value of a length is 122 millimeters. This is the easy one. The measured value is 120 millimeters. I calculate the absolute error, relative error, and the percentage error. Yes. Now the absolute error, I'm going to call it A error, or absolute error, is going to be 1. The true value of 122 minus 120, you get 2 millimeters. The relative error is going to be equal to the true value, which is, I'm sorry, the error, absolute error, which is 2 over the true value, which is 122, gives us 0.01639. And the percentage error is going to be this multiplied by 100, so it gives us 1.639%. Now, let's start with average power. And so, yeah, let's go. Yeah, RMS values and so. Okay, let's go to RMS values and sinusoids. Yeah, let's start with the easy one. A US outlet voltage is 120 volts RMS, and it's sinusoidal. Find the peak voltage amplitude, or V peak, VM. Yes, perfect. So Vm is going to be VRMS times square root of 2, which is going to be 120 times square root of 2, gives us 169.7. Keep in mind, VRMS in sinusoidal is always greater than Vm. So if your options is 169, 112, 95, the one that it's greater is always the answer for sinusoidal. Vm is always greater than RMS in a sinusoidal. Now, instantaneous power, a resistor R is driven by Vt of 24 cosine of omega t. Determine the current I, the instantaneous power Pt, the average power absorbed by the resistor as well. Yes. How much is it?
The average.
The P average. Yes, perfect. Yes, that is correct. Okay. Now, to find IT, the current, it's going to be equal to V over R, Ohm's law. And what is V? It's 24 cosine of omega t, and R is 12. So this would be equal to 2 cosine of omega t. Now, PT is equal to VTIT, or VI, which is going to be equal to the current times the voltage. So 24 cosine of omega t times 2 cosine of omega t. So this would be 48 cosine in the power of 2 omega t. Now this is the instantaneous power. We have to find the average power. So we can, find the average power different ways. We can do derivation, we can do integral. There are a couple of ways to solve it. The easiest way is to use derivation, and if I remember the equation right, cosine square of omega t is going to be equal to 1 plus cosine of 2 omega t divided by 2. So 48 cosine square of omega t is actually equal to 24 times 1 plus cosine of 2 omega t. We don't care about this cosine part. Why? So the result would be 24 plus 24 cosine of 2 omega t. What is the average of cosine and sine? 0. It's always, because the cosine is like this, and the average is always what? 0. Average of these two and this. So an average of a cosine sine is always 0, and we're left with what? 24. So P average is going to be equal to what? 24. And we're going to find the average. By the way, this is average over a cycle. It's 1.5 cycles because it's going to be different. This is average over a cycle. When we say average, it's going to be average over a cycle, because when it goes to infinite, you're going to have that same. Yes?
The equation specifically current, at least the equation I remember, it was Vm over R times cosine of Wt, but also plus phi of V. Do you need to include that phi? Or
No, that's a shift. We didn't put an n in the beginning in the system. So yeah, no, that's a shift. No. That's going from negative infinity to positive. It's not what we call a causal, signal. It's, starting. We want to just find it on 1p. That phi is for shifting. Yeah, thank you for bringing the question. Let me see. 9. Yeah, we solved 9, 10. Let's see how much time we have. Yeah, I guess that we can solve another one on average power. Let's solve 10. Given Vt is cosine of omega t, this one is the one that related, then that's the reason I want to solve this one as well. Another reason. Vt is 120 cosine of omega t plus 10 degrees, and it is 5 cosine of omega t minus 20 degrees. Calculate the average power delivered. Now in this particular situation, there is a phase shift between the voltage and the current. So either the system could be lagging or leading. So when we have a phase shift, then we're going to have, a different average power. Now, when we have phase shift, you can find P average using this, the equation that we had. This is for a three-phase AC power, by the way. It's going to be half of Vm Im cosine of phi. And we already went through this equation in the lectures as well. In the previous one, both of them were same phase, so V and I were synchronized, I could say. Oh, by the way, just for the reminder, phi is theta V minus theta I. Don't confuse that. Theta V minus theta I. Yes. Yes, perfect. Do you need more time or do you want me to solve it? Okay. Thirty degrees. Half of what? Do you want me to solve it? Okay. So phi is equal to it's the phase difference. It's 10 degrees minus negative 20 degrees, which gives us 30 degrees. And then the average power would be half of Vm, which is 120, Im, which is 5, Vm and Im, cosine of 30 degrees, which gives us 300 times 0.866. This is what I calculated, and maybe double check my calculation. And it's almost 259.8 watts. Did you get the same number?
Why is
Again, this equation that I mentioned here. When you have the cosine, it's going to be the half of. This is the average. Now, for the previous one, just let me go back a little bit. For the previous one, this was your voltage. This is your current, and they are synchronized. They don't have any phase shift. And this red would be your power, okay? When you multiply them together, okay? The red would be your power. This one, your voltage looks like this, but your current looks like this. So where you have maximum voltage, you have, and by the way, the current is actually much less. It's like 5. So it looks like this, something like this. Okay, same frequency, but this one is, the phase has shift, so you won't have the maximum peak at the maximums. And I already solved it for this. You have a cosine term, you have a sine term. Sine term, when it's average, it becomes completely 0, and you're left with a cosine term. Okay. Did you write this down? Can I go to the next question? Okay. I want to be able to solve the last 3 as well. This is this question number 11 is a 3-part question. A balanced 3-phase source has a line to a neutral voltage magnitude of 120 volts. Write the phase voltage phasors VAN, VBN, and VCN. It's a very easy one. First part is very easy. Solve first part. So VAN is going to be 120 with a degree of 0 degrees. VBN is 120 with a degree of negative 120 degrees. And VCN is 120 with a degree of negative 240 degrees. Now, second part. We want to find, using the same balance source, it's a 120 volt source, determine the line-to-line voltage for VAB, including both magnitude and angle. Okay. So VAB is going to be equal to square root of 3 VLN with a degree of 30 degrees. VAB, the magnitude only, is going to be square root of 3 times 120, which gives us 207.85 volts. By the way, this is a star connection or Y connection if it's not mentioned. And a delta connection, it's equal. Now the angle is 30 degrees. So VAB is going to be 207.85 with a degree of 30 degrees. Let's go to the last part. Already, I think, solved this. This is an easy one. Let the phase voltage peak value be at 170 volts. For a 6 hertz balanced three-phase source, write VAN, VBN, VCN in time domain form. Again, pretty easy. Okay. What is VAN of T? It's VM cosine of omega t. Am I correct? What is omega? 2 pi f, yes. 2 pi times 60, which is going to be 377. Now, if I gave you t period, what would f be? If, for example, t was like, yeah, like something milliseconds, f is equal to what? 1 over t. So you could find t that way. In other words, omega is 2 pi over t, which is the period. Now, VAN is going to be 170 cosine of 377 t. VBN would be the same, but plus or minus 120 degrees. So 377. And VCN is going to be again the same thing. 377 minus 240 degrees. So all of them same, just the phase shift. Now that we have a little bit of extra time, I want to solve another problem as well. So this one is a good one. A galvanometer has a full scale current of 1 amp and internal resistance of 2 ohms. Design a shunt so the instrument becomes a 5 amp full scale ammeter. Sorry.
Need to draw the circuit or just give you the value of the shunt?
Yeah, just give me the value of the shunt resistor RS. Enable one as a
Oh, no.
what did you get?
Oh.
Perfect.
That up.
Great. Yes. Remind me to give you the extra points on you. Do you need more time or do you want me to solve it? Yeah. Okay, let's first visualize it. We have a galvanometer and at full scale, it has an internal resistance of 2 ohms. And I have this galvanometer. And at full scale, the current that it passes it's 1 amps. Meaning when you put 1 amps, it's going to go, you know, to its maximum at full scale. Now, we want to design it in a way that we can put 5 amps into it. Okay. So to do that, if I put 5 amps to it and the maximum, that the galvanometer could take is 1 amp, it's going to destroy the galvanometer. So what I have to do is I need to put a resistor in shunt with the system. Okay. And now I want to determine how much voltage, how much is this resistor going to be? I'm going to call it RS or shunt. RS, let's put it RS. So at 1 amp, if I measure the voltage without the resistor, at 1 amp, the voltage, so at full scale, let me write it down. At full scale, I is 5 amps. This is what we want. So I want 4 amps to go through RS. So I, at full scale, if we have 5 amps coming in, the maximum that this could take is 1 amp, and the rest should go through the R shunt. Okay. So I of the shunt should be 4 amps. Now, without the shunt, V of the galvanometer is going to be I of the galvanometer times its R, which is going to be 1, the maximum current that it's going to pass it without this, times R, which is 2. Now, this gives us 2 volts. So I have 2 volts on the galvanometer when I have maximum current passing through it. What is the relation between the voltage of the with its internal resistance and the shunt voltage? What is the voltage of these 2 points? I'm going to call it AB, and these 2 points, CD. The same. They are in parallel shunt, so they share the same voltage. So VG is actually VRS as well. Now, if I want to find RS, I can do it using Ohm's law, or VS over IS. VS is 2 because it shares the same voltage, and IS is 4 amps. So this would be equal to 0.5 ohms. So the resistor of the shunt would be equal to 5. There are multiple ways to solve it. This is one of the easiest ways to solve it. I just wanted to, simplify it for you. So when you add a resistor, they're going to share the same voltage, but it's going to, divide the currents between them. And that way we can find. Here we mentioned how much current we want to pass RS. In the exam, I may give you RS and say, okay, now RS is like 0.2 ohms. Find the current that is passing through RS, something like that. Okay, I don't think I have time to go through another example. Or do we? Let me see what let me go through a very, small question. Easy question. Question number 7. I think this is the last one that we can say. A length is reported at 120 millimeter plus negative 2%. Determine the corresponding uncertainty range, the range that we have. The range of error, they also say it is also. So first we have to find the percentage of the error compared to the total. So 2% of 120 millimeter is 2.4 millimeters. So the range is going to be equal to 120 minus 2.4 and 120 plus 2.4, which is going to fall between 117.6 and 122.4 millimeters. Okay, that's it for the review session. That concludes the review session. Fortunately, we were able to solve a majority of problems. Your exam again is going to be, next class is going to be your exam. I've already posted an announcement for the online students. If you have any questions, please let me know. And please study your homeworks, and also the problems that I solved and the solved problems on your lectures as well. Thank you so much and have a great